Hello all. This video continues the introduction to groups by talking about two key examples. We'll be talking about some very specific cases for these two classes of examples of groups. So first one is permutation groups. Specifically, I'm going to be looking at group of permutations on three objects. So I've got three objects here, a red square, a green square, and a blue square. I want to see what happens. Permutation is essentially reordering this line of three objects. So if we look over here, I've got this 1, 2. This is saying I want to trade the places of the thing that's in the first position with the thing that's in the second position. So red would go to position 2, The green thing would go to position 1. So my end result is going to be here, start with green, then red, then blue. So we've got that. Let me move this back to where it was. So I'll scooch red back to where it started, green back over here. So now what happens if I apply things sequentially? Actually, I probably shouldn't have done the work that I just did, because the way we write these things, we want it to echo function composition. So if I'm applying these permutations to my objects, I'm going to start by applying the thing on the right, the innermost thing, and then work outwards. So I'm going to apply 1, 2 to this first. So switch the things in position 1 with position 2. This goes here, and then that goes there. And then I'll apply the thing in the outermost position 2, 3. So I'm going to swap the things in the second and third positions. So this goes here, and then this goes here. So end result of applying these permutations, I've got green, and then blue, and then red. We said that groups were all about looking at ways we could add, so to speak, objects together. Here we're adding together the two different permutations by performing one after another. So essentially we're adding 2, 3 to 1, 2. For groups, though, we want to get a permutation out. We did get an arrangement of the objects. The thing that was in position 1 over here got moved to position 3. So I'm going to say the way that I use this cycle notation here, I'm going to start out with the object 1. I'm going to write down what position it goes to. So the thing that I started with goes to position 3. And then I want to say, okay, whatever I write after the 3, that's what place that the thing went to, that was in position 3 went to. So blue was in position 3. It's now in position 2. So I'm going to write down a 2 here. We can double check. The thing that was in position 2 was green. Now it's in position 1. That we've already written down a 1, so I'm going to close this parenthesis. We'll say that this 2 goes back to 1. So that would be how to write down this permutation in this particular notation, but we have also figured out that when we add together the permutation 1, 2 and the permutation 2, 3, we get 1, 3, 2. But take a look at what happens when you add together. This is going to be your exercise. Try adding together these two things in the opposite order. I've put all this attention in how we're moving inside to outside. Does it actually matter? Try out what happens when you first apply 1, 2, and then 2, 3. See in this particular case if you end up getting the same thing or not. If you always get the same thing, the group is abelian. If you ever don't get the same thing, then it isn't. One last thing to look at. So I will swap my squares back to their original places. Interesting. Anyway, so I've got my permutation 1, 2. So if I take this and move it here, and I'm claiming that this is a group, we can say, like the identity permutation that's just not swapping anything. If you do any permutation and then don't swap anything, or if you don't swap anything, then do the permutation, you just get the other permutation that's going on. But we also claim that there should be inverses. So this 1, 2, there should be something that I could do to get back to my original ordering. Here, it's easy enough. I just need to swap these two back. So if I do 1, 2 again, the thing that's here in position 1 goes to position 2. The thing that's in position 2 goes back to position 1. Oops, if I didn't. Oh well. Let me move that over here and then shrink it again. Oh well. Now I've swapped back to the original position. We've seen that if I perform 1, 2, and then 1, 2 again, that is just going to be the permutation that does nothing. So that does count as the inverse. One could permute more than 3 objects. So we say that this Sn is the group of permutations on n objects. There's a lot more to study with permutation groups. This was just a flavor of what some of the key considerations look like. We've got one other group that I want to introduce. And again, I'm introducing a specific example of a larger class of groups. So say that you've got a square. I've got here a square that has some distinguishable things in its corners. We're going to look at the different ways we can flip and rotate this. So I'm actually going to open this up with my photo app. You're welcome to follow along, although I'd say if you're doing this with a photo, save a copy so that you're not inadvertently doing anything weird to a photo that you care about. But anyway, if I quick do a split view and pull up my photo app here. So if you see here, my photo app lets me rotate this square. So we're going to call R a 90-degree. This is counterclockwise. Let me edit this. So we'll say that this is going to be rotating counterclockwise. So that would be one thing. When the way we add things together here is by performing one action after another. So like if I wanted to add a 90-degree rotation to, I've got this ability to flip across the vertical axis, that would be my result. Let's go back to the, I'll just click reset. That's not what I wanted to reset. Split view, go back here, go back to my photo, and go back to edit. So, turn that back into a square. Okay, so anyway, we've got this ability to rotate and to flip. We're claiming that we can add them together. Let's first see what happens when I add some rotations together. So like if I add this is one rotation. If I've got 2, we've got R squared, which would be a 180-degree rotation. If I rotate again, that would be R cubed. That would be a 270-degree rotation counterclockwise, or a 90-degree rotation clockwise, however you want to frame it. But if we rotate a 4th time, we're back to where we started. So I would just call that my identity element, the way of flipping and rotating that does nothing whatsoever. So we've got all of these. We've got this vertical flip. There are 3 other possible flips we could flip across, say, the horizontal line that I'm sketching in right here. So if I were to do that, I would call that a horizontal flip. So I'll say that H is going to be this thing but horizontal. Horizontal line. If we were to, for example, if I did do this one rotation and then this flip, what we've actually done, if we compare this to the original, we've managed to flip this diagonally. So we've ended up flipping my picture across that diagonal right there. So I'm going to, if we think about like linear algebra matrices, the diagonal that I'll draw here, I don't know, I guess I'll use red. That would be what we would call the main diagonal. So let me say that, sorry, let me go back to my usual writing color. D is going to be a flip across the main diagonal. And then we'll say that D prime is going to be the flip across the other diagonal, or the off main diagonal. So we've got these four. We've already established, I had gotten to this place here by saying that we had done a, yes, clockwise rotation, counterclockwise rotation, and then flip. So we figured out, for example, that, and I'm going to write it left to right. I do apologize for the inconsistency between these different groups, but yes. So one rotation and then one vertical flip is going to get me D prime. We figured out, for example, that if we were to rotate something three times, it would undo rotating once. So again, I invite you to keep on experimenting, potentially using a photo app like this. Figure out what all possible combinations are, whether it's possible to get any other types of flips. There are also, we were working with a square. In my notation, I use D4 to indicate that. Dihedral group on an object with four sides. If you replace this square with another regular polygon, so like, for example, a regular hexagon, you would get more possibilities for rotations and reflections. And so that would be, in my notation, if you're using a hexagon, D6. We've got many other dihedral groups. There's, again, a lot more to study, but at least you have some awareness of how this addition works for this thing that really does not look like addition. So, thanks for watching. Catch you in the next video.